All right, let's talk about transactions. So up to this point, we have been interacting with the databases as a single person. Right? You either at the console, sending command lines to select, to insert, to update at the MySQL command line interface, or as applications that you write in Java, where you use JDBC or JPA or Mongoose to interact with the database. But for now, up to this point, it has been just one single thread, one single process talking to your database. And but more commonly, what an actual database would be handling dozens, hundreds, thousands of processes that are talking to it simultaneously, right? Or if it's just one single application, it might be an application that is multi-threaded, where each thread might be getting a hold of a connection, right, and talking to the same database at the same time that some other thread is also talking to the same database. So whenever we have concurrency, we always have to consider the possibility that these threads and these processes might be stepping on each other's toes, right? That they might be reading or updating or manipulating the same data, right? And as you might have already seen in other courses, whenever you have a shared resource, there's always a risk of inconsistency, right? Depending on the way you need to order the operations and how to handle locking the resource so that you don't have folks that are at the same time writing other folks that are reading the same piece of information. So the same exact issues arise when you have a shared database, right? So today we're going to be talking about using transactions as a mechanism for handling this multi-process, multi-threaded use of access to the database. So here's an illustration that you might have multiple processes, multiple threads. Some are doing selects, some are doing inserts, some are doing updates, some are doing deletes, all on the same table, maybe on the same row, maybe on the same field. Right? So certainly this chaos needs to be managed. Right? We need some way of dealing with this intersection. And you need some traffic cop in the middle to say, well, you stop while somebody else goes, right? Otherwise, there'll be some crash. So whenever you have a shared resource, you need some way of stopping others while letting some others use the shared resource. Right? So how do we do that? So transactions is a mechanism, is a technology that allows us to serialize, meaning create a queue or create some mechanism by which some resources, some accessors need to wait for everybody else to go, right? Either we have those in real life, either as stop signs or traffic lights, or some cop in the middle of an intersection making things worse, right? That and everybody else just needs to wait. There's a queue. Now we have to weigh the different things that we want to achieve, right? One of the things that we want to achieve in the first place is the optimal use of a resource, right? For instance, that's why we're using multi-threaded, right? Multi-threading is a mechanism that allows us to use resources efficiently, right? So that we don't have necessarily folks waiting on each other, right? That things can occur simultaneously, on their own little space, so that you don't have these queues that have to wait on each other, right? We want that. We still want that efficiency of multi-threading, but we also need to consider facts where you have shared resources, right? So it's okay if everybody is doing their own thing and not stepping on each other's toes. That's okay. But when it comes to things that are shared, we need to make sure that we don't have inconsistency. So imagine we all had this large, Google document that you're working on the first couple of pages and you're working on the conclusions down below. And that's okay. There's no inconsistency. There's no collision of folks working on the same resource because they have their own little section. But when we're both working on section 1 on the same paragraph, then there might be an issue there, yes, on who wins. So same thing here. We have, in this case, would be tables, right, views and whatnot, right, and we might be writing or reading the same table, writing or reading the same rows or the same fields. If we're in different rows, perhaps in the same table, then it might be okay, right? That we let folks, interact with one portion of the table while others work on some other portion of the table, some other list of rows. But if they're going to be working on the same, then we need to consider the possibility of collisions. Yes. Also, if the operation is, for instance, just plain old reading, right, reading the data, then there is no risk of inconsistency, right, of collisions, because we're all reading the same information. It's the same. It's the same for all of us. But if you have folks that are writing or manipulating the data and folks that are reading from the same row, then there's the risk of inconsistency and collision. So we need to have some mechanisms that would allow us to arbitrate, right, or manage this potential chaos. One of the challenges is that oftentimes operations, a particular operation might actually be a logical operation, might actually be multiple operations or interactions with the database. So consider, for instance, when you need to transfer money from one account to the other, right? Transferring an account actually translates, even though it's a logical single operation, right, of transferring money between two different accounts, it's actually implemented as two separate operations. Right? You need to update two accounts. One you need to decrement, right, and the other one you need to increment. So it's two operations that we would like them to be logically one, but we know that they're actually implemented as multiple operations. Yes? So transactions allow you to group multiple operations as if they were logically one, right? So that if any one of the operations fails, right, it should be considered as the entire operation failing. For instance, if I was able to, as I am transferring money from one account to the other, and I was able successfully to decrement one of them, right, it would be erroneous to fail, not being able to perhaps increment the other account, right? If I fail because there was a server error, or there was a SQL error, or there was I just crashed in between the two operations, right? The entire transaction should fail, right? It should roll back the changes of the original one where it was decremented, and put it back to where it was, right? So that we don't lose any money in the transaction, right? So transactions allow you to keep track of a temporary update to a database, and only make that temporary update, only make it permanent once you have confirmation that all the operations were successful. Okay. Another analogy might be that I'm visiting my daughter for college, and I need an airplane ticket. I need a place to stay. They don't let me in the dorm. And I need a car to drive when I get to Chicago, right? And if I don't have any of those, if any one of those three I fail to acquire or successfully confirm that I have all three, I'm not going to Chicago, right? If I have an airplane ticket and I have a hotel, but I don't have a car to get around, I'm not going, right? And notice that any one of those three transactions, they're separate transactions that they could all succeed independently of each other, right? I go to Expedia, and I was able to book a hotel and an airplane ticket, right? And I actually paid for them, right? And with a credit card, and I have a confirmation number that I'm leaving, right? And that I have a room for me to stay there, but I don't successfully am able to acquire a car or somewhere, a way of mobilizing myself in Chicago. Yes, and so. And I just wasn't able to. I need to be able to undo, right, my airplane ticket. I need to be able to undo my hotel reservation, right? And usually these operations allow you to do that, right? They are permanent, insofar as they allow you to give you maybe 24-hour notice, or they allow you to, within some some window, it allows you to undo whatever operation you had done, even though it was fairly permanent, right? The changes, even though transactions are not typically long running that deals so many hours or days or weeks. Transaction are typically things that occur almost immediately or just milliseconds. But the analogy stands, right? I need to be able to roll back or go back to a previous state where none of the operations had occurred. Right? So transactions allow you to treat the operations as an atomic single unit, and you're able to fail the entire transaction and all the operations that were within the transaction. Yeah, so that's the example of booking a hotel, airlines. So the purpose is that you need to be able to recover from any failures of any one individual operation, so that the entire unit of work can be rolled back and go back to a previously consistent state. Right? So if, for instance, we were transferring money, $100 from one account to the other, we don't want to be in an inconsistent state where I was able to deduct from one account and I wasn't able to deposit into the other one. Right? Somehow we lost $100, right? In the meantime, as we were going trying to do the transaction. We say that transactions have these properties. They're acid in that they're atomic, meaning we can treat multiple operations as if there were a single atomic operation that it is not divisible in its constituent parts. Right? It's an all or nothing. Right? You're actually able to do the inserts, the updates, and the deletes as if it one single block. Or if any one of them fails, I'm just going to throw away all those changes and go back to where I was. Right? So I can atomically demarcate where it begins and where it ends, group together a whole bunch of operations into a single one. So an atomic all or nothing. Consistency, meaning that it's able to go from one consistent state to another consistent state, right? Where everything adds up, right? There's nothing missing, right? That if I do identify that I am in an inconsistent state, that I can always roll back and go back to a previously consistent state. Right, that I can backtrack, I can see the history of all my changes and where it failed, and where I see that I went into an inconsistent state, meaning somebody's missing $100. Right, I was able to deduct, but not increment. Right, I can always roll back and say, well, I want to go back where I was. Something like in a Git repository, I can throw away and go back to a previous state of my application. Here being the database. The other one is isolation, where you have multiple operations, multiple processes, multiple threads that are all of them at the same time concurrently operating on the same piece of data. Now, they themselves should not worry or have to worry about other threads. They should feel as if they were the only ones operating on whatever data they're operating on. Right? They should not be worried that other processes are operating on the same database. It should look to a thread. It should always look to a thread as if it were the only owner of that data, even though there are multiple threads running simultaneously. Right? So the transaction should allow a thread to operate in isolation. That's what we mean, right? That it can work logically as if it were the single owner of that piece of information. And durability is that whatever updates or deletes or inserts or data that we have created or manipulated will be here tomorrow or a week from now. Even if the database fails and crashes, and we can always recover and to go back to a place where we have the data that we had there originally. We say that transactions allow you to group multiple operations into a single unit, and the way it does that is what we call demarcation. It demarcates. It's able to say when a transaction begins and when it ends, right? And anything in between the beginning and the end of a transaction is a group of operations that are treated as a single unit. Right? We call that demarcating the transaction. And we do that with operations such as begin, commit, and rollback. Right? Begin tells the database, hey, I'm beginning a transaction, meaning all the following operations should be treated as a single unit. Right? I'm going to insert, I'm going to update, I'm going to delete. Right? But those changes of inserting, updating, and delete, those changes are only temporary. Right? They won't be made permanent until I demarcate the end of that transaction by either saying commit, right, or rollback. And by committing, I'm saying, well, all those inserts and all those updates and all those deletes, I want to make them now permanent. Right? Make them now permanent, and that's the end of the transaction. Or, all right, by whatever reason, I might say, oh, I'm having second thoughts about all these inserts and deletes and whatnot. I want to roll back, meaning throw away all those inserts, throw away all those deletes, throw away all those updates. Right? Go back to where you were when we began the transaction, right before we began this transaction. Okay? So those three are the operations that allow us to demarcate the beginning and the end of a transaction. Begin, commit, and rollback. Right? You can either do it at the console, as you are interacting with the database manually, or through some API that allows you to, will give you some function or some method that you can call using JDBC, where you can begin, commit, or roll back a transaction. JDBC, by default, up to this point, we have been using the default transactional behavior that JDBC uses out of the box. Right? If you don't say anything, JDBC uses a strategy called auto-commit, transaction auto-commit. Right? Meaning that each individual operation, whether you do an insert, an update, or delete, it automatically commits right away. Right? It begins a transaction, does the insert, and then it commits the transaction immediately. So that's not really that's not any better than that doesn't allow you to group multiple operations. Right? Each operation is individually its own little transaction. Right? It doesn't allow you to group multiple operations into a single transaction. So later on, we'll talk about its limitations and how we can turn it off and use more powerful interactions with the database. So let's take a look at all the things that could go wrong when we are not using transactions. Right? One of the things that we could just imagine is that if somebody is writing a piece of information and is not yet made permanent, I might be looking at data that is stale, right, or that is has not yet been committed. Right? So, for instance, somebody might be updating somebody's salary and calculating the average, and depending on that average, I'm going to give somebody a raise or whatnot. Right? So I might be in the process of calculating those things and grouping and averaging out and things like that, and updating certain salaries, but not until I commit, those changes are not made permanent. Right? So I'm busy doing this. In the meantime, somebody might be coming and doing a select on those same rows that I am in the process of updating that I have not yet completed. Okay? So it would be unfortunate for somebody who's reading information that is not yet permanent, that is only temporary, and that it might be rolled back. So meaning that there might be making decisions on data that is actually stale or that has not yet been made permanent. Okay? So there are many things that could go wrong, right, on the certain decisions that you might make based on bad data. Right? So let's just consider multiple things that could go wrong. Right? And the things that could go wrong depends on what we call the isolation levels. Right? By isolation levels, we mean is it all chaos and everybody does whatever they want? Right? That means that we're not isolated whatsoever. Right? Everybody is writing and reading and doing whatever they want at any time, right? And overriding their changes. And that's just chaos. Okay? So that's one extreme. No isolation. Everybody does whatever they want at any time. So that's one extreme. The other extreme is, no, everybody's going to have to wait. Right? We're going to put a traffic cop, and whenever I'm I'm going to operate or read or write to a table, I'm going to put a lock on it, right? To guarantee that I am the only one who's looking at this data, right? That's operating on that data, and not until I say I'm done, right? I will and take that lock away, right? Will everybody else have a chance to use that same table, right? And that scenario, we need to have some kind of queuing mechanism, right? Where you have a thread, the first thread that gets there gets a lock, right? Operates on that table, inserts, updates, deletes, does whatever they want with that table, and not until they get to the end, they release the lock. Right? Meanwhile, all the other threads that were trying to access that same table are queued up, are waiting. Right? They're idle. Right? They're just waiting for this lock to be released, and waiting for when the lock gets released, the next thread in that queue gets a chance to get at that table. In that scenario, we have created a queue. We have serialized something that would have been simultaneous concurrent, right, operation. We have instead made it in a serialized. We have serialized one. You go first, then you, then you, then you. We have created a series, right? So those are the two extremes. Okay. Now, in between those two extremes, there are other scenarios that are not as chaotic and not as serialized. Okay. And one in the extreme of the serializing the data of the access, there is no risk of inconsistency because only one thread is ever touching the data. It's as if I'm working in Google Docs and I open it up and I'm the only one touching it, right? So there's no risk that somebody might come in and trample over my paragraph that I'm writing over it. Once I'm done, I release it, and then the next person can come in and make their edits. Yes? Right, there's no risk of inconsistency. In the other case, if there's no isolation whatsoever, everybody could just write whenever they want, and we can trample on each other. But in between, there's a sweet spot, right, that we can choose where we don't have total chaos or total total totalitarian, right? So here are some names that allow that list the various types of things that could go wrong based on the level of isolation, right? Between in that range of isolation levels. So let's take a look at some of the things that could go wrong. Let's first consider some scenarios that can illustrate the things that could go wrong. Right? Here we have two threads, right, running on two different transactions, and they're both operating on the same piece of data. Okay, so here we have two threads. One of them is trying to do one thing, and the other one is trying to do a different thing, but they're both reading and writing the same piece of information. One of them is trying to swap professor sections, meaning I'm teaching section 1 and you're teaching section 2, and maybe for a different course perhaps. And I'm teaching 3 courses and you're teaching 2 courses, and we're in the process of switching sections. I'm going to teach the undergrad and you're going to teach the graduate. But the operation would be to unenroll me from one section, unenroll you from that section, and then just enroll me in your section and enroll you in this other section. There's 3, 4, 5 different operations that have to occur. Yes? And it might take a millisecond or 2 or 10 or 20. Right? At the same time, concurrently, there's another thread that is running, right, that is calculating the bonuses for this semester for teachers based on their workload. How many sections do they teach this semester? Okay. Now it would be very, very unfortunate if somehow these threads overlap each other. Okay, where one of them starts, but before it gets a chance to finish, right, this other thread comes in and reads data that has not yet been made permanent. Right. It would be very unfortunate that the first thread starts, it unenrolls me from section 1, unenrolls you from section 2, right? And before it gets a chance to enroll us back into our sections, my number of sections goes down from 3 to 2, yours goes down from 2 to 1, and this other thread comes in and calculates, right, what our bonuses are going to be based on an erroneous count on how many sections we're both teaching. Yes, it reads and then it goes on merrily, unbeknownst to it that somebody else was writing to that same information. Yes. So in that sense, one of them read data that was not yet committed. Okay. And we refer to that as a dirty read, data that has not yet been committed. Right? You were reading data that was still temporary. Here's another example where a student might be making a purchase, a $50 purchase, and they're going to credit their university account, and the transaction is for $10. So they have $50 in their account, and so one of the transactions reads the $50, right, and it has a copy of that $50 in the CPU in memory, and it deducts the $10, and then it makes a reasonable assumption that the database still has those $50, and it updates it to $40, right, and that's reasonable. If it's that single thread, it makes sense, right? The algorithm makes sense. But what if you have multiple threads running where one of them reads 50, right, and it's calculating how much it's going to deduct, yes, but at the same time somebody's making a transaction where they're depositing $1,000 into your account, right, and it starts and it successfully completes, and now in your account there's $1,050, not $50, $1,050, right? But this and it completes successfully. Where the original thread has $40 and goes and updates your transaction, your account to be $40. So there's $1,000 that are lost somewhere, right? So we call that that's also an inconsistent state, right? It would have been nice for the thread to be able to lock that information, right? So that because I'm not yet done, right, I am assuming that the $50 is still $50. We say that I am assuming that read that I made originally, that if I make a different read now, I would get the same information. I would get the same $50, right? We say that we're assuming that first read is repeatable. Right, that I can repeat the same read and I would get the same data again, right? So you're assuming a repeatable read, okay? But because the database was not set up to guarantee a repeatable read, right? We get these types of inconsistencies, right? Yeah. So T1 assumed that it was going to be able to do it was going to be able to repeat that same read. The other scenario might be where I make a read. I read a select statement where I have a range, or I get multiple records that meet my criteria. I do a select statement where I want to retrieve all the employees that make a salary between a particular range, between $25,000 and $50,000, and it comes back with, I have these 100 employees that meet that criteria. Yes? Now, while I have that information in memory that I know there's 100 employees, right, at the same time, somebody might be inserting new employees into the database that would have met my criteria. Yes? It's almost the same as a repeatable read. Okay, almost the same as a repeatable read, but the difference is that one of them is the repeatable read error or inconsistency is for a particular row, for a particular field. Whereas when we're talking about a range of multiple rows that meet a particular criteria, we call that a phantom read, meaning that there might be multiple records that I missed somehow, right? That I read there was 100 records, and I'm making a decision based on those 100 records, but actually there might be 101 or 102 or 103 because somebody is updating and inserting into my database, right? Or deleting, perhaps, right? Going down from 99, 98, 97, right? So my stale information about that select statement might make me make wrong decisions. Here's an example where I do a count of the number of students at the end of a year, and from several fundraising that we've done throughout the year, we've been able to raise $100,000, right? And we want to break it. We want to split it up amongst all the students in the student body. There's 1,000 students, so we make all right. So everybody's going to get $100, yes? And but between the time of making the read of calculating that there's 1,000 students, there might be new enrollments into the department. And now we have perhaps 10 new students. Yes. So when I go and make the update of depositing $100 into each one of those students, I'm going to actually, instead of depositing into 1,000 students, I'm going to deposit into 1,010 students. So somehow I'm going to be off by $1,000 there, right? I'm going to be depositing more money than I should have, right? For 10 new students that were not there in the original count. Make sense? Right? So those three are the most common types of inconsistencies that we try to avoid. One is dirty reads, meaning I'm trying to read something that has not yet been made permanent. Right? The other one is repeatable read, meaning I'm making an assumption that the data is not changing on me. I read it, right, and I'm assuming that it's still there, that it's the same value, that if I read it again, I'm assuming that's going to be the same value as I read a couple minutes ago or a couple seconds ago. And the last one is phantom reads, where I do a query based on some range, right, and I'm assuming that those records are the same records. It's almost like a repeatable read, but with a range of multiple records. Yes? Those are the three types of inconsistency. There are many more. Right, but those are the most common ones that we try to avoid, right, or fix, right? And the different types of isolation levels are target each one of them in appropriately. Right, so let's look at the different isolation levels that might fix each one of these.